Hello everyone, and today we'll be learning about something very new in physics. It is related to magnet and magnetic effect. So before we start, what are magnets? Right? So magnets are nothing but those materials which attract iron or some other materials towards or away from itself. That is called as a magnet. Magnet is a material itself and it is going to attract or it is going to push away iron and some other material towards itself or away from itself. Magnets come in various shape. The two type of shapes which I put on the picture is a U shape and a bar shape. This is called as a bar magnet, and the U shaped is called as a horseshoe magnet. This is a bar magnet and a horseshoe magnet. Because it looks like a horseshoe, therefore it's in the same shape as the horseshoe. So it's called as the horseshoe magnet. Now a magnet is always internally divided into two parts, north and south. Okay, and the horseshoe magnet also has north and south. One end will behave as a north and the other end will behave as a south, and it will attract or repel certain materials towards itself. So let's look into certain properties, few properties of a magnet. Okay, and then further we'll talk about what we say, how to identify or how to understand how strong is the magnet and how to figure out to find out the strength of a magnet or the force applied by the magnet. Okay, so before that let's go into and check out the rewind and revise the properties of a magnet. Now, all of you have seen a compass. Nowadays, we have compass in the mobile phones also. The compass has all the four directions and there is a needle which is placed inside the compass. Compass is also a type of a bar magnet. It has a small needle and its end point approximately towards the north and the south direction. Right? If you look in this magnet, it's a north here and a south here. This is the north and this is the south. So this needle of the compass is south. Why? Because the opposite charges attract or opposite poles attract, correct? And the like poles repel. So if this is this red color pin on the needle of the red color needle will be north, then it should be deflecting, but it is towards the north of the bar magnet, therefore it has to be the south pole. So the two important properties of a magnet is that it has two poles, like poles repel and unlike poles attract. Okay, sorry for the spelling, attract, right? Let's look into an activity to understand how like poles repel with each other and how like poles attract with each other. The second important definition is whichever direction, if you allow the magnet, if you just hold the magnet suspended in air, whichever direction the north pole or the north side of the magnet is indicating or is being displaced is called as the north seeking direction, and the other side is called as the south seeking direction. Clear? So let's look into the activity. So as you can see here, there is a freely suspended magnet which is pointing north south. So they have actually hung the magnet in the air on a tripod sign and they have left it there. So for a few seconds it will start dwindling or it will start moving in a round circular fashion, and then it will stop at a particular time slowly, and north will be in one direction and south will be in the other direction. So the direction in which the north is being pointed is called as north seeking direction or the north pole, and the other one is the south pole. So let's look into the details. So the end of the magnet which points towards the north is called as the north seeking pole. Now, even if he tries to move the direction, it will come back and stick back to the same north position because it will balance and arrange itself. Now this is called as the compass needle, which also has a north pole and the south pole. So it keeps it's dwindling or shaking till it doesn't get the exact north pole and south pole. Again, this is the north pole and this is the south pole. Right? Next. Unlike poles attract and like poles repel, we are looking into this thing. So they are taking one already suspended in the air and the other they are holding it in the hand. So this is the south pole of the magnet which is hanging, and the north pole is brought near it. You can see how quickly it gets attracted. So the south pole is and north pole gets attracted to each other. Similarly, once again, if you bring the south, the north is swinging and dragging towards the south pole. Yes, so unlike poles attract each other. Similarly, in a needle, north and south pole, this is the north and this is the south. You can see the south is attracted towards the north and it is vibrating constantly. The moment he is turning the magnet, the person is turning the magnet towards south, the north pole of the needle is attracted towards the south pole and it keeps vibrating because of the force of the magnet. Similarly, when you please place it down, you can see very clearly how south pole is repelling each other, because like poles repel each other. Attraction of unlike poles. So the activity clearly showed that unlike poles attract and like poles repel. Now we are going to talk about something called as magnetic field and magnetic field line. Again, let's look into an activity to understand what is being done, and then I'll explain further. Now on a plain sheet, they have taken some iron fillings. Iron fillings are called as shredded or pieces of iron, very minute pieces of iron, but not powder of iron. It's called as iron fillings, a little bit tiny pieces of irons. Okay, so you can observe that the magnet will attract these small pieces of iron towards it. Can you see it? Sticking towards the north and the south pole and kind of making a thread-like structure, right? That was bar magnet. Now we are placing the horseshoe magnet, and you can see the iron filling sticking towards the bar magnet and forming the thread-like structure, right? Similarly, if the whole magnet is placed inside it and rotated, you can see it has been completely covered, but still the iron fillings are attracted or attached to the corners, not in the center. The north and the south pole are completely filled. You may feel that these lines which are being formed are like mixing together, but they are not. They are still separated from each other, right? So similarly, we'll be using a horseshoe magnet to do the same process. Do Here it very clearly we can see that the iron fillings are attracted to each other, but the only thing is we feel as if these the iron fillings are getting stuck to each other and they are mixing with each other, but no, they are more attracted towards the iron pole. Can you see this U-shaped kind of a stringy structure? That is because the north pole and the south pole, in between the north pole and the south pole, the magnetic fillings are aligned, means arranged. So this is how we saw. These are more powderish, more powdered iron fillings, but the same condition. We do feel like they all are stuck together and they are mixing together, but physically the individual grains are separated from each other. So as we can see, the iron fillings arrange themselves in a pattern. And the pattern is that the iron fillings will be running from north pole towards the south pole, which in the next activity I'll be discussing. So we also saw the horseshoe magnetic. Can you see some iron fillings being attracted between the north pole and the south pole of the horseshoe? Clear? So the magnet exerts its influence in the region surrounding it. Therefore, the iron fillings experiences a force. The force thus exerted makes iron fillings to arrange in a pattern. The region surrounding a magnet, in which the force of magnet can be detected, is called as the magnetic field. Means the space around the magnet where we can feel that the force is being applied. That area or that space is called as, that particular area or region is called as the magnetic field. And lines along this iron filling which align themselves represent the magnetic field line. So if you can see here, these are the magnetic field lines. Can you see here? These are the magnetic field lines, right? Correct? And they are, as you go far away from the magnet, the dust is not being aligned. They are just still scattered. But as you go closer to closer, the magnetic fields are more jammed up. Why? Because the force of attraction of magnet is more stronger when it is nearby and it is less when it's far away. So for this magnet, the region where the magnetic field can be, or the force of the magnet can be experienced is this area. Similarly, if you look at this magnet, the force of this magnet can be experienced around this area. Okay, let's look into the activity where we can identify, or we can mark out the region where the magnetic field is present, the strength of a magnet. We can do it by using the compass. So here what they have placed is, they have placed the magnet north pole south, and they are placing the compass. Okay, this is the real picture which I have depicted in this one. Okay, so this needle is the south, which is red in mark, and the white one is the north. So you can see it's south and north attracted, still south and north attracted. When you're placing like this, just parallel to the magnet, it is going parallel. Still the south is towards the north and the north is towards the south, right? So when you try to draw this, connecting the lines, you will always get the field coming out from the north and going inside the south, top as well as in the bottom, the same thing. So normally the direction of the magnetic field line is, it is going to emerge out or come out from the north and merge out into the south. Again, it's going to come out from the north, okay, and merge out into the south, right? So the direction of the magnetic field is taken to be the direction in which the north pole of the compass needle moves inside. Can you see the north direction of the north pole moving inside? So if you can see here, the white is the north, so it is going like this and coming back like this, right? Moving inside. Same way in the bottom also, it goes like this and comes back inside. Okay, so that is the direction of the magnetic field lines. Even in this figure, they have shown it's coming out from the north and moving towards the south. Okay, therefore it is taken by convention that the field lines emerge from north pole and merge at south pole. Inside the magnet, the direction of the field lines is from south to north. Inside, it's from south to north. It moves in this direction. Okay. Thus, magnetic field lines are closed curve. Inside the magnet also, they are moving from south to north, and outside it is from north to south. So it's a complete circle. North to south outside, inside south to north. So it's a complete circle. Therefore, they are closed curve. They have both direction and magnitude. Therefore, they are called as the vector quantity. I'm sorry. They are called as the vector quantity. Clear? Now, the relative strength of the magnetic field. Sorry for the interruption. The relative strength of the magnetic field is shown by the degree of closeness, how close the magnetic field lines are. That will tell us how strong the magnet is. So the field lines are stronger, means the force acting on the iron fillings or on any other magnet is greater. That means the field lines are crowded. When you see all the lines crowding together, that means the field or the magnetic effect or the magnetic force is very strong. No two field lines will ever cross each other. If they do, then the compass will always point both the directions in one side, which is not possible. So we just saw what is magnetic field lines, what is magnetic force. Magnet applies force. That force can be understood through magnetic field lines. The more closer the magnetic field lines are, the more they are stronger. The magnetic field lines are always parallel to each other. They never cross over with each other, right? Let's look into the last activity. Before we end the session, or before I end this video, let's have a quick look at what the activity is again. So we are sprinkling some iron fillings on a piece of paper, and we are going to spread it all over and then wait. So on the sheet of paper, we have actually put some iron fillings. Okay, now we are going to place the magnet in center of it. Okay, so when we place the magnet, the iron fillings should align in a particular pattern, right? So let's look into it. Now when they place it, right, now we are going to literally bang it so that the particles of iron fillings can move towards the magnet and can create the field lines, right? So can you see the field lines? The more closer they are near the magnet, they are more crowded. The more far away, if you look, they are less crowded because the strength of the magnet is less far away from the magnet. Okay, Clearly, near the magnet, the field is very strong, means the force of the magnet is very strong. Whereas far away, the magnetic field effect or the force is